welcome to NPTEL MOOC on fiber optic communication systems and techniques. In this module, finally we are going to apply the ideas that we talked about in the last two modules to understand lasers or to finally discuss what makes a laser. Well, we have all the ingredients here. We have a 3-level system. Okay. So, I am not being very specific about what kind of system this is, okay, because these ideas apply to any system that can exhibit these 3 levels, and these levels are with the energy E1, E2, E3. This is the material or the gain medium which is contained in the cavity. So, these green curves are actually for the mirrors and they serve to kind of give you the feedback. So, that is the photons that are emitted will be made to go back into the gain medium again and again and again, so that you can have this huge buildup of stimulated emission. And of course, you cannot just keep making them go back and back without actually supplying an external pump, and that is what we are actually going to do. So, we are going to supply an external pump which is shown in this red line. And what does this pump do? This pump allows the atoms in the energy level E1 to get excited to energy level E3. So, please note, this is very important. You are not sending in the pump of an energy such that it is actually going to get to E2. You are sending the energy such that you are giving it more energy, so that these atoms in the ground level do not go to E2, but directly jump up to the level E3. And the interaction that governs, which goes from energy level E1 to E3, is something that we already know. It is given by minus B12 phi p delta f n1, and instead of writing this as phi 1 p b1, or sorry, this is b13 because this is the level you are going from 1 to 3. So, instead of writing this as b13 delta f phi p, I am going to introduce a simplified notation called as AP. Please do not confuse A with the earlier Einstein coefficient A. This is a different coefficient. This is the absorption coefficient, or this is actually what we call as the transition probability. And this probability, why it is so, or the transition cross section or the absorption cross section, why this is called as a cross section, why this is a probability, is all something that we do not want to worry about. You just take this AP as a shorthand notation for B13 phi p delta f, and the absorption process is governed by minus AP times N1, which of course will deplete the population at the energy level E1 while increasing the population at the energy level E3. Okay. Of course, once these electrons go to the energy level E3, they have two possibilities. Some of them spontaneously come down from E3 to E1. We will call that as N3 divided by tau 31. Now, what is this tau 31? Well, we know that spontaneous emission is governed by the coefficient A21 times N2 for a simple 2-level system, where A21 was called as the Einstein coefficient. Instead of writing this as A21, we simply write this as 1 by tau 21. It makes sense because N2 by tau 21 will tell you the rate at which N2 is decaying because of the spontaneous emission. Numerator is the density, population density, and denominator is the time, which is what the left hand side was actually, right. So, it was change in N12, or the rate at which N1 was changing with respect to time. So, numerator was density, denominator was time. So, all the spontaneous emission terms are actually written as 1 by tau, with the subscript telling you which energy level to which energy level we are considering. Therefore, this particular interaction, the spontaneous interaction from E3 to E1, can be written as N3 divided by tau 31. Okay. Similarly, and this is much more probable because atoms go or like to go from E3 to E2, and the reason why I have put a wavy line here in these two, because these reactions are non-radiative. That means they do not actually give out any photons, but they serve only to deplete the population. Okay. This reaction on the other hand will give out spontaneous emission. So, I will have to change this one. So, instead of a wavy line, I have to make this a straight line. Okay. So, now this interaction from E3 to E2 is a non-radiative one. So, that would be N3 divided by tau 32. So, notice that we are writing this as tau 32 because you are going from energy level E3 to energy level E2. from E2 to E1 you have two more interactions. One is that E2 atoms in E2 drop down to energy level E1 and that one will be phi p delta F B21 times N2. Okay. So, I have written this as phi p delta F B21 as the phi p delta F B21 times N2 as the stimulated emission case, and just like previous this one, this is not phi p because this is not the pump photon density, this is just phi delta F B21 N2 and phi delta F B21 or B12 because B21 is exactly equal to B12 can be written as AL. Okay. So, what you have is AL times N2 and this is a plus as far as the energy level E1 is concerned, right. So, for the energy level E1 it loses population because of the absorption which is given by minus AP N1. It gains population because of stimulated emission which is written as AL N2, and then you will also have spontaneous emission from N2 which would be N2 divided by tau 2 1, and then you will have spontaneous emission down from E3 which would be N3 divided by tau 3 1. Okay. So, this is how the total population density is actually changing. So, if you write down the equation as to how energy or population level in energy level E1 changes, you can write this as dN1 by dt is actually equal to the pump absorption. So, that would be minus AP N1 minus N3. I will tell you why I am writing this as N1 minus N3. So, this is the absorption, pump absorption plus spontaneous emission down from energy level E3 to 1, plus you have N2 by tau 32 which is spontaneous emission, plus you have stimulated emission. So, emission is represented by L which is the lasing action, and this is N2 minus N1. Okay. The reason why I have written as N1 minus N3, right, is simply because since this laser is operated at a temperature greater than 0 degree Kelvin, right, there will be thermal energy, and because of thermal energy the initial populations at N3 and N2 are non-zero, okay, and you are not interested in the actual energies or actual populations, but you are interested in the population difference that comes about. So, what is the contribution of the absorption, how does this go away? Because these photons can be absorbed and some photons can be absorbed, reabsorbed to make them go from E3 to E1, the actual change will be from N1, instead of N1 it will be N1 minus N3 times AP. AP stands for the pump absorption, okay, and it is in the normal case N3 will be much smaller than N1, okay, and of course this is what equilibrium actually tells you, that N3 is much smaller than N1. Therefore, the effective change at the level N1 that is happening is given by minus AP N1 minus N3. Okay. However, for the spontaneous emission does not depend on N1 when you look at spontaneous emission from E3 to E1. So, therefore, this is just N3 by tau 31, similarly N2 by tau 32, but for the lasing or the stimulated absorption or stimulated emission, what you have is the effective population difference N2 minus N1 times whatever the pump or the emission cross section is what would count. So, the equation that we have written, in this boxed equation will tell you all the different terms that will serve to effectively change the population level at energy level E1. Okay. So, dN1 by dt consists of these 4 terms where AL is defined as phi delta F B21 and then AP is defined as B13 phi P delta F. Of course, B13 is the same as B31 and B21 is the same as B12. And there is an important thing here that I want to mention. Phi P stands for the pump photon density. Okay. So, this is the external energy coming in because of the pumping process. Okay. So, this is pump photon energy density or the pump energy density to be this one, whereas the photon density phi without the subscript is actually the signal photons, right, because these photons are the result of stimulated emission between the levels E2 to E1. So, there is no P here because P would refer to interaction between E1 and E3. Okay. So, there is a difference between phi P delta F and phi delta F. So, please keep that difference in mind. Of course, what will happen, these photons which are now stimulated emission effectively would start to travel, they would hit the mirror, assume that the mirrors have reflection coefficient of say gamma 1 on one side and gamma 2 on the other side, and after they have travelled, once they have hit the reflection, these photons would travel back towards the gain medium, where they will further cause stimulated emission to occur, and these stimulated emission photons or stimulated emission photons would again travel towards the second mirror, undergo a reflection say at gamma 2 and then come back. So, inside the cavity they are circulating back and forth, thereby increasing the total population density of the signals. Okay. But because you want to take this thing out also, right, you do not want all the radiation or all the power to be there inside the cavity, you want some of that power to actually come out of the cavity. What you do is you take gamma 1 to be around say 99%. Okay. So, that 1% of the radiation is actually tapped out, and you take gamma 2 to be 1, which means there is 100% reflection on one facet and there is about 99% reflection on the other facet. There is nothing sacred about 99%, you can take whatever the percentage. Of course, what you have to ensure is that if you start taking all of the power out, then there will not be any power inside to sustain the stimulated emission. So, you have to just simply avoid that condition. Okay. So, typical numbers of 1%, 10% or 35% out and 50% out are quite common. There is of course a certain relationship which tells you that you can extract certain maximum power at an optimum power coupling ratio. Okay. So, you can maximize that power coming out of the laser by carefully choosing that gamma 1. Okay. Higher values of or higher tapping out or the higher coupled numbers like 50% or 90% simply does not mean that you will be able to always get more power, because remember, any power that you take out of the cavity means there is that much amount of power less in the cavity to sustain this stimulated emission. Okay. So, you do not want to get too greedy, get some power out by 1 to 10% and then leave the remaining so that it can sustain this stimulated emission. Anyway, so I have written the equation for N1, and I would leave as an exercise for you to write down the rate equation for population level N2 and N1. I will give you hints, okay, so that you can write this, and then I will the sign here, please you have to write down the sign here, and this is N2 by tau 2 1, and again the sign here you have to write down, okay, whether it is plus or minus, and then I will say this is AL N2 minus N1. Okay. And then finally, you have dN3 by dt, I will again write down this one. So, minus AP N3 minus N1, I will leave the sign here for you to pick, this would be N3 divided by tau 3 1, and I will again leave the sign for you to write down, and I will say N3 divided by what. Okay. So, please fill up these equations, they will allow you to understand how the population levels are changing in energy levels E1, E2 and E3. And once you have written down these equations, the next step would be to try and find out what would be the minimum pump power required, so that you can actually have population inversion. So, the goal of this exercise was to ensure that you are pumping in certain amount of photons such that the population level at N2 will increase compared to N1 and N3. So, when you have strong pump, okay, or sufficiently strong pump just after the critical pumping, then N2 will be greater than N1, and the difference N2 minus N1 we will denote it as delta N and call this as the population inversion. Okay. So, what you actually expect is that this delta N will be negative when the pumping is not very strong, and as the pump increases at a certain critical or the threshold pump power, delta N just becomes equal to 0, which means N2 will be equal to N1, and once the pumping increases beyond this threshold value, remember AP is proportional to phi p delta F B12 or rather B13 or B31, whatever that is, right. So, it is phi p delta F, it is the pump photons that we are talking about. So, once the pump photons sufficiently exceed then exceed the threshold value, then delta n becomes positive and you will actually have laser action here. Unfortunately, there is no laser action when AP is less than the threshold value. Finally, in all those equations that you have written, you will find out that at population level 3 there are two different spontaneous emission factors that are present. So, one is level 3 to level 1. So, that is governed by 1 by tau 3 1 and then you have 1 by tau 3 2. Okay. So, you can define the effective lifetime of a photon, that is the characteristic time scale over which an atom at energy level E3 would decay down to energy level E2 or would decay down to energy level E1 as 1 by tau 3 equals tau 3 1 by tau 3 2. This is like your parallel resistances being added and this is given by tau 3 1 tau 3 2 divided by tau 3 2 plus tau 3 1. This is 1 by tau 3, or the effective lifetime tau 3 is given by tau 3 1 tau 3 2 divided by tau 3 2 plus tau 3 1. Now, if you look at a typical laser, what you want is most of the atoms which are at the ground level E1 to end up in ground level E2. Okay. But because of absorption, E1 atoms in E1 go to E3. Now, you have two options, right. So, E3 to E1 can drop down and that characteristic time scale is about tau 3 1 and the characteristic time scale from 3 to 2 is tau 3 2. If you ensure that this tau 3 2 is very small, that is why we had put them closer together, indicating that these two actually are quite close in the sense that the lifetime from 3 to 2 transition is much faster, or in the sense that it is much smaller. It will not spend much time to, or it will not take much time for the atoms in energy level E3 to drop down to E2, okay, but it will take a long time for them to drop down from T3 to or E3 to E1. Okay. So, if you take this condition, then what you see is that tau 3 2 is very small compared to tau 3 1. Okay. So, because that is very small, so tau 3 1 is much larger than tau 3 2, the effective lifetime tau 3 can be approximated as tau 3 2 itself, because tau 3 1 is larger in the denominator compared to tau 3 2. So, this will go away and then tau 3 1 cancels out and then you get tau 3 effectively as tau 3 2, and this is desirable. This is in fact the critical condition that is necessary. If you have a matter in which this transition time is much faster compared to this transition time which is much slower, then you will not be able to sustain population inversion. So, this is bad for our laser application. Okay. So, that is one condition that we wanted to talk about. Of course, you could generalize this results to 4 level system. I am not going to do that one, but what I am going to do is that I want to consider what happens in the steady state condition in which all of these populations dn3 by dt or dn2 by dt or dn1 by dt, all these terms are actually equal to 0, and when you set the first one to 0, what you will find is that you can write down n3 in terms of n1. So, you will have AP divided by AP plus 1 by tau 3 times n1. Okay. So, this is a simple exercise. Again, you can show this, you just have to set dn3 by dt equal to 0, and once you have done that one, you can get a relationship between n3 and n1. Now, typically what happens is that once the pumping is critical, okay, n3 will be much smaller than n1. Of course, n3 was always smaller, but you would have expected that because there is absorption that n3 can become higher than n1, but in the steady state condition that would not be so, because most of them would be absorbed. Atoms from E1 to E3 would have dropped down to E2, okay, because of the spontaneous decay from 3 to 2. So, effectively in the equilibrium condition, the population level N3 is quite small compared to population level N1, but N1 itself should be smaller than N2. So, that delta n, which is the population inversion, will be larger, and you can actually show by setting dn2 by dt equal to 0 that N2 is given by N1 AL plus N3 divided by tau 3 2 divided by AL plus 1 by tau 2 1 if there are no additional losses, then total population density will be the sum of the population levels at 1, 2 and 3 levels, okay, and this should not change, this should remain constant. And when you look at delta n and normalize it with respect to t, you will see that by using this equation and the other equation for n t, you can see that this will be given by A p times 1 by tau 32 minus 1 by tau 21, okay, minus 1 by tau 21, 1 by tau 3 divided by, I will leave this as an exercise to find out what is the denominator. Of course, we do not really need to know the denominator as importantly, but this equation delta n normalized with respect to n t is very critical for us. Why? Because it allows us to look at the relationship between tau 32 and tau 21, okay, and it will also allow us to find out what is the critical pumping rate or pumping required, so that this population level delta n or the population inversion delta n will be greater than 0. So, that is the sufficient or that is a necessary condition is that A p should be greater than a threshold quantity. And what is the threshold quantity? Well, for delta n to be positive, the numerator has to be greater than 0. So, once you set the numerator greater than 0, you will see that A p 1 by tau 32 minus 1 by tau 21 must be far greater than 1 by tau 21 divided by tau 3. You can write down these equations, and what you would actually find out is that from energy level 3 to energy level 2, tau 32 is much smaller than the lifetime from 2 to 1. Okay. So, you have this tau 21 which is much longer. So, which means that most of the atoms which go from 1 to 3 and from 3 to 2 would remain in this energy level E2. Okay. So, that the population inversion of course can take place. If they do not remain and then just keep falling down to N1, then there is no population inversion, no laser that can be sustained. Right. So, clearly tau 32 must be much smaller compared to tau 21. Okay. So, because tau 32 is much smaller compared to tau 21, 1 by tau 32 will be much larger than 1 by tau 21. So, that you have A p being much larger than 1 by tau 21, because 1 by tau 32 will actually, oh sorry, this is 1 by tau 3, but anyway this can be approximated and into tau 32 and then can be cancelled out. So, what you actually see is that the condition on the pumping rate is that it has to be much larger than 1 by tau 21. So, this is an important condition, and if you are not clear about 1 or 2 points about this one, please go back and solve this equation for yourself. You will and impose the condition that tau 32 is much smaller than tau 21, and you will actually be able to get this expression. Okay. Sorry, this is not greater than, this is actually approximately, right. So, A p threshold we will call this is 1 by tau 21, because tau 32 is much smaller than tau 21, and in this equation 1 by tau 32 being larger than 1 by tau 21 means A p divided by tau 32 is much larger than 1 by tau 21 divided by 1 by tau 3, and you can cancel off this guy with this one, this anyway goes to 0 and A p will be approximately equal. The critical value will be equal to 1 by tau 21, but you of course need to pump beyond this particular thing. So, what you want is population inversion to be sustained, which means that population level N2, most of the atoms which are excited from E1 to E3 and then drop down to E2 must spend most of their time in the energy level E2. They should not drop down quickly, they should spend their time here, and your pumping rate must be sufficient such that this condition is satisfied, and the critical value for that should happen is approximately given by 1 by tau 21. So, now you know that if you take a helium neon laser, you take a Nd:YAG laser, you take an erbium doped fiber laser, you can then go and find out what is the lifetime of E2 to E1, the two energy levels that are involved, ground and the next higher level, okay, and then make a guess as to what would be the pump rate required for that for the laser to be sustained. Okay. So, this is very interesting calculation, and the history of this calculation is also very interesting. I will not be able to go to that history, but if you are interested you can look at a book called Lasers by Hecht. Okay. He discusses this theory, this is entirely, I mean he discusses these ideas or the history of how these ideas of laser came about in a very interesting manner. So, you can take a look at that one. Sorry, there is two books, one is Lasers and the other one is City of Light. So, you can refer to either of the two books for a fascinating history of these ideas. Okay. Of course, what we have is the threshold value. At the threshold value, of course, delta n will be equal to 0, okay, which means you have just gotten about the value of delta n. But it turns out that the value of delta n just being equal to 0 is not really the minimum required value. What you want is delta n to be greater than certain critical value. We will not derive what is that critical value here, that derivation is little too long, but you need to see that just because you make delta n equal to 0 does not really give you laser right away. You have to make this one to be greater than or equal to a certain critical value. Okay. I will give you the expression for this critical value, that is given by 1 by tau p h times b V a. If you are wondering what these terms are, b is just a term which we have written for B12 or equivalently for B21. V a is the cavity volume. Okay. So, you have this cavity which has a certain area. So, this is the cavity, right. So, this cavity has a certain cross sectional area and it has a certain depth d here or d prime here, and this cross section is say some a d prime. So, this product of a d prime to d prime is what we have called as the cavity volume, and b of course is this one, and pH, tau pH is the lifetime, which is approximately equal to tau 21 in our case. Okay. So, this is the this is also sometimes called as the, actually this is not equal to tau 21, this is slightly different. We will simply call this as cavity lifetime. Okay. This cavity lifetime has to do with how much I mean it has to do with the reflection coefficient in the first mirror, the passage or the gain here, the attenuation in the medium which is not gain, and then there is a reflection back on to the second mirror gamma 2, right. So, cavity lifetime is essentially the effective lifetime of a photon which is stimulated emitted, okay, but it would kind of statistically remain in that cavity before escaping out from the first mirror. Okay. So, mirror with a reflection coefficient that is less than 100%. So, it is not exactly tau 21, I am sorry, tau 21 is the lifetime of the photon or the characteristic time of the photon where it will drop down from energy level E2 to the ground level E1, and this critical value which is also equal to the steady state value surprisingly is something that is necessary so that lasing can happen. Okay. So, we have discussed these 3 level lasers. There are couple of additional things that we could discuss, but unfortunately I do not have time in this course to discuss those things. What I would now like to do is to look at basics of semiconductors in the next module, so that we can apply these ideas that we have talked about, population inversion, rate equation, and how exactly or what exactly will be absorbed, and is that absorption process same as what we have been talking about. There you will see that in semiconductors the concepts of electrons and holes become very important, and they have these different characteristics that go with them, and how they would affect lasing is what we are going to see in the next module. But for this module, if whatever the exercises that I have given you, please solve them. They are simple, they have to just rearranging the terms in an equation, and solving them will allow you to understand these basic principles of the lasing that would happen, and that would be applicable for any laser that you can consider, with some modifications of course which are specific to the lasers themselves. So, thank you very much.